Hi, everyone. I'm Molly James. I am a PhD student at the University of Connecticut. I'm also a physicist, but not of space, but of the ocean. So it's my pleasure to introduce Dr. Lachlan Lancaster. We know each other. We went to high school together. Lachlan went to Carnegie Mellon first and got his Bachelor's of Science in Physics, then went to England to pursue a master's at Cambridge University, then came back and did his PhD and another master's at Princeton University, and is now currently a junior fellow at the Simons Society of Fellows at Columbia University with Professor Greg Bryan, studying star formation. Tonight, he'll be talking about dark matter and dark energy. Without further ado, Dr. Lachlan Lancaster.
Thank you so much, Molly. That was very weird to hear my life read in front of me. Thanks so much for having me. It's really, really cool to be here. It's really hard to come up with, when you're making a slide deck about dark matter and dark energy, to come up with a picture to put on the front. Because this is sort of a talk about the things that you can't see in the universe. I chose this picture. This is a picture from the Webb Space Telescope of a galaxy cluster. This is a cluster of quite massive galaxies. The whole thing probably weighs about 10 to the 14 solar masses. So that's 100 trillion masses of suns in this cluster of galaxy. That's so much mass and so much small space that, and we'll come to this a little bit in the talk, general relativity predicts that matter bends the fabric of space. It changes the way that light travels through space. And that is actually what we're seeing. You can see these little wispy arced things around here. Those are galaxies that are actually behind this cluster of galaxies, and their light is being bent by the gravity of that cluster, being lensed by it, and it's coming around the galaxy and lensing back towards us, and that lensing process stretches out the galaxy. And the only reason that it's able to do that, most of that matter, that 100 trillion solar masses of stuff, is in dark matter, stuff that we can't see. So there is dark matter in this image, but you can't see it directly. You can only see it proportionally to what it does, which is, as we will come to, sort of everything we know about dark matter. I want to get to what are dark matter and what are dark energy. This is something that is, it looks like what you would think dark matter would be, right? Stuff you can't see. This is actually a cloud of molecular gas within our galaxy, and that molecular gas has enough dust in it that dust blocks light from getting to us. So this is just a giant cloud of gas sitting in our galaxy that is dark enough that it's blocking starlight from the other side of it. I sort of wanted to sort of introduce that as sort of a way of saying, here's something that looks like, what you might think of as dark matter or dark energy. But these things that, as we will sort of get to, these things are really sort of placeholders for things that we don't understand. So it's good to approach this subject with a little bit of humility and remember that, and I think that's partially why they're also interesting, why people like thinking about dark matter and dark energy. They're kind of sort of these things that we can't understand, and that's why we're interested in them. They're kind of mysterious. Mm-hmm. But Einstein liked to say that the coolest thing about the universe is that it's understandable at all, that there's anything that we can, there's no reason it has to be, right? It's important to keep that in mind, I think, when you're thinking about these things. Philosophical maybe, but this is the School of Athens, which is a painting by Raphael. In the center of it are probably some of the only actual people who lived in Athens in this picture, Plato and Aristotle. One of them, Plato, is pointing to the sky, and Aristotle is pointing at the earth. They're right at the center. And I'm really kind of stretching things a bit here, but the general idea was that Plato, he thought of things as sort of in this pure realm of forms, sort of the ideal world. He didn't like thinking about things that were actually, because the world itself is too messy, right? And Aristotle says, look at the ground, we need to base our theories of how we understand the world based on the things that we actually see. And as we'll see, when you come up across these things that we don't fully understand, there's sort of different perspectives on how to look at these things. There's, we use the world as we already understand it to explain the things that we see, or do we change our theory of how the world works fundamentally? Do we change fundamentally how things work? I'll just say that there are these two sort of perspectives, but if you want to consider something science, if it's a scientific question, then it must be testable, it must be provable. You must make predictions that can be tested and changed. I just really like this quote. There are more things in heaven and earth than are dreamt of in your philosophy. So it's always, again, important to keep in mind that we're approaching stuff that we don't understand. So keep that in mind. This is from Shakespeare, from Hamlet. Okay, so story time, actually getting into things. So before the modern dark matter problem, or the modern dark energy problem, there were two sort of interesting stories that I think will help us a lot in understanding actually the things that we wanted to talk about, which is the dark matter and dark energy. So I'm going to talk about two stories within the history of science. The first is the precession of Mercury, and the second is this sort of static universe. So first, the precession of Mercury. In 1609, Johannes Kepler used some observations from his advisor at the time, Tycho Brahe, to discern that the orbits of the planets around our sun were not actually circular, but they were elliptical. And they were elliptical with one focus of the ellipse was centered at the sun. That was a big change from just being circles, but he couldn't explain in particular the motion of the orbit of Mars without making it elliptical. Or Mars's orbit is actually the most elliptical other than Mercury, this orbit. A few years later, but still in that same century, Newton came up with his theory of gravity that perfectly explains why all orbits around objects like that should be elliptical. That just falls out of this force is equal to this gravitational constant, the product of the two masses of these things, divided by their distance squared. That, it turns out there's some math behind it, but basically that will perfectly explain why orbits are ellipses. The problem is that that's only true if there's only two bodies. And in our solar system, there aren't just two bodies. There's the sun, and all of the other planets, and the other planets act to perturb that sort of perfect system. So if it was just this perfect system, you would have this perfect elliptical orbit and nothing would ever change. Because there are all these other objects, you actually get precession movement of the orbit due to all these other gravitational interactions. And in 1859, Urbain Le Verrier, who was a French astronomer, he measured the precession of Mercury's orbit, which is the most elliptical orbit of any in our solar system. And he measured it, and he took into account the motions of all of the other planets and Newton's law of gravity. So he did this whole calculation. He found that he was off by this tiny fraction. That's 38 arc seconds. That's the angle subtended by a hair held at arm's length every century, every 100 years. But he only had a few years of observations of this thing. But he was so confident in his calculation that he said there has to be another planet that we can't see. Why did he think that? Well, a few years earlier, this same guy had used the anomalies in the motion of the orbit of Uranus. He basically to the same degree tracks the motion of Uranus very precisely. And he, using just that and math, precisely predicted where Neptune was and led to the discovery of Neptune. Neptune was discovered using math, which is pretty cool. He basically sent a letter to a bunch of astronomers in Germany, and they looked at it that night and discovered Neptune. Yeah, it was within 1 degree of where he said it would be, which is, so okay, now we have a little bit more confidence in this guy, Le Verrier. Maybe he knows what he's talking about. So he measured the precession of this orbit, and he predicted that there was another planet around, and he called that planet Vulcan. Proposed the existence of this new planet, Vulcan, which is where Spock is from. Of course, you all know that there is no planet named Vulcan, not unless we've been hiding it somewhere. But you didn't learn about a planet called Vulcan. in any sort of class. So what's the solution to this? Okay, 1915, Einstein, for completely different reasons, proposes a new theory of gravity. Basically just based on thought experiments that he did in his head and knowing a lot of differential geometry. This equation is Einstein's field equation. It fully describes the theory of gravity, just like that sort of Newton's equation that I wrote down. It's really shorthand for a 10 coupled partial differential equation, which would be a total nightmare to write down, which is why I write it like this. But the point is that just using this theory of gravity, if you apply it, if you try to use it to try and derive something like Newton's force law for gravity, in the limit where it should apply, you get the normal mass equation, g times mass divided by r squared, but then you get these little correction terms. And those little correction terms, most places where gravity is not very weak, where gravity is very weak, they're not very important. But they change the orbits. Orbits are no longer perfect ellipses, but they do precess, even without any other problem. And it turns out that if you just include this prediction, you predict what the precession of Mercury's orbit should be beyond what it's the effect of the other planets, and you get 38 arcseconds per second. So Leverrier was perfectly correct. He just didn't have the right theory of gravity to understand. So, okay, we've come up across our first problem of dark matter, right? We see something in the universe and we say there has to be, first of all, there was one solution where dark matter was real, right? There was stuff that we couldn't see. Neptune was there, but we hadn't seen it before. In this case, we proposed dark matter to be there, but we actually, it wasn't dark matter. It was that we needed a new theory of gravity to understand how things were going on. This leads us perfectly into story time number 2, which is the static universe. So in 1915, again, exactly what I just said. Einstein develops this new theory of gravity. A few years later, in 1922, a Russian physicist, Alexander Friedman, used Einstein's equation using some assumptions about sort of the structure of the universe on large scales. You can derive this equation, which I won't explain too much, but basically on the left side, you have that stuff basically says this is the rate at which the universe is expanding is equal to stuff in it. The main thing here is that what this equation says is that if there is stuff in the universe, then it cannot be static. It needs to be expanding or contracting. If the right side is non-zero, then the left side has to be non-zero. At the same time, this Georges Lemaitre, who was a Belgian priest and physicist, basically came to the same conclusion. He, independently of Alexander Friedman, who was in Russia at the time and this was a while ago. It took a while for things to get around, but he came to the same conclusion and told Einstein, and Einstein said, your calculations are correct, but your physics is abominable. Because the universe is eternal. It's always been here, it's static, it's not moving, and we can't have it be expanding or not. So I will add in a constant factor into my equations, and that'll fix everything. Okay, we put in this other term, and basically now you can still have stuff in the universe, but now if it's canceled out by this, you can have this side be 0. That's how science should work. Unfortunately, not true. So 1929, just a few years after Friedman and Lemaitre, Edwin Hubble looks up, he measures the distances to what he called nebulae at the time, but were galaxies. And he measured how far away they are and how fast they are moving away from us. And he discovered there's this linear relationship between how far away something is and how fast it's moving away from us. And if you think about if you were to have like a little ball that sort of exploded or something, and you did a freeze frame at a few seconds after that happened, and you precisely measured where things were and how fast they were moving, you would notice that the further away you are, the faster the things are moving away from that central point, right? Because they had to get further in the same amount of time. So they must be moving faster. So what this is basically, and there's a lot more math behind it, but what this had actually been predicted by Lemaitre in his paper. He said we should be able to go measure the velocities of galaxies and their distance away from us, and we should see them moving away from us faster the further away they are. And so what this did was show that the universe is not static. So we had, again, this problem of the physics was telling us that this thing was happening and it didn't fit in our box of what we wanted the world, the universe to look like. So we changed the physics, but that wasn't the right thing to do. Okay, so we talked about these story times, past story time. Let's come to the evidence for these things that you came here to learn about in the first place. What are these things that we call dark matter now or dark energy now? And why do we think they're real? Okay, 1933, only 4 years after that last thing, which is, this is a while ago, but also not very long ago. I think my grandfather was like in college at this point, so not very long ago. This guy, Fritz Zwicky, he's a Swiss astrophysicist who has worked most of his life at Caltech. He measured the motion of galaxies in this galaxy cluster, the Coma cluster, so another galaxy cluster like what was on my first slide. And he noticed that they were moving too fast. So in particular, you just imagine that if there's only a set amount of gravity that's pulling stuff in, if things are moving around too fast, that gravity can't trap them and they'll just fly away, right? So the fact that all these things are in one place means that they're probably gravitationally bound to that object. So just measuring the motion of those things, you can infer how much matter there is within something. So in particular, you can basically get this from Newton's gravitational force law, that if you have some mass, this capital M here, within some radius or distance, then the things within that sphere should have a velocity that's something like this, the square root of the gravitational constant times the mass divided by r. And all that I'm saying here is that the velocity of things gives you an idea of how much mass there should be in something. The very key point to our understanding of why we think dark matter is a thing, okay, is this equation. I should say Fritz Zwicky, as you can kind of tell from this picture, this is like this canonical picture of him. He was not the most pleasant person. And in particular, he liked to call people spherical jerks because they were jerks no matter which way you looked at them. And so he wrote this paper, and not a lot of people listened to him because they didn't like him very much, which is a lesson for everyone. So basically what he said was he saw these velocities were much larger than they had to be, and he said there has to be a lot more matter in these clusters than we're seeing in light in order to explain the velocities of these stars. And because he was Swiss, he called it Dunkelmaterie, which is just dark matter in Swiss German. Leaping forward to the 1970s, Vera Rubin, this is sort of the same basic picture that we were just talking about, is that the velocity of things should tell you about the mass enclosed within galaxies. And in particular, Vera Rubin, she didn't use sort of these whole galaxies, but she measured the velocity of gas in the disk of the galaxy. And in particular, as you go further and further out in the disk of the galaxy, how fast is that gas moving away from us or towards us? This is called the rotation curve of the galaxy. And that's what's being shown in this plot. This is the y-axis is this circular velocity, that's VC, the circular part, as a function of the radius, the distance away from the center of the galaxy. And in particular, if you only accounted for the amount of mass that comes from the stuff you can see, the light, the stars that we have there, and also the gas. So galaxies are not just stars, but there's lots of gas and dust. So Vera Rubin was using this radio astronomy, actually. So she was using the fine structure line of hydrogen, which is in the radio. There's lots of hydrogen gas in galaxies, so you can do this pretty well. I mean, it was new at the time, but this is textbook stuff now. So basically, she went and measured so this is for a particular galaxy, NGC 6503. The data points here are that data that she took. And the dashed lines and the sort of dotted line here is what you would expect if the only stuff that was contributing to the gravity that was pulling this stuff around was the stuff that you could see, the stars and the gas. But as you can see, it gets up to this top point and then it just stays high. And so in order to explain that, you add in another term, missing mass that you can't see, which is this halo. So I've tried to draw a line, dark matter, halo. So dark matter, and to this day, we understand dark matter is sitting in sort of halos around the galaxies. So this was observational point of evidence number 2, but Vera Rubin was a much better messenger for this than Fritz Zwicky was. And sort of, it was controversial still, but throughout the 70s into the 80s, people finally came to understand that dark matter is a real thing. Dark energy, what is our evidence for dark energy? So we talked about before how Hubble showed that if you measure the velocity of galaxies, the further away they are from us, the faster they're moving away from us. So that showed that the universe was expanding. In 1998, these 3 physicists who led teams of, I should say with all of the people that I'm talking about, almost it should be implied, but they're not the only person who did the work. There is usually a lot of people that goes into the discussion. And so I'm a little bit contributing to this idea that science is only done by sole geniuses, which is definitely not the case. But it's an easier story to talk about, which everybody thinks that it's just these sole geniuses. But usually there's huge teams of people behind it. And that's definitely true in this case. In 1998, these 2 separate teams announced results that showed that not only was the universe expanding, but its rate at which it was expanding was actually accelerating. So it's expanding and it's speeding up in its expansion. And that's shown in this plot, which is very hard to figure out. So I changed the labels. This is that same sort of Hubble diagram that I was showing you before, except it's flipped. So before it had distance on the bottom, velocity on the top. Now we have velocity on the bottom, distance on the top. And what we're showing is that the further away you are, the faster you are moving away from us. So these different lines, it seems like they might all agree with this, but there's actually statistically significant evidence that the only way that you produce this data is through having an extra term in your equations, which you see is this omega lambda. So these omega m terms, they're basically telling you about the amount of matter in the universe. So that's both stuff that we're made out of and dark matter. And by this point, 1998, people believed in dark matter. Everybody was on board for dark matter. And this omega lambda is telling you about the dark energy in the universe. But basically, you need this to explain what's going on. Coming back to the cosmological constant, basically the way that you explain that the universe is accelerating in its expansion is by adding this lambda term back into the equations, but with the opposite sign that it had before. Because you don't want to stop the universe from expanding, you want to accelerate its expansion. There were a lot of articles at the time that were sort of like, Einstein was right all along, which is just completely missing the point of how what he was thinking about and what he was trying to solve. But I don't think he would have agreed with that. But basically, one way to solve this problem of the universe accelerating in its expansion is by adding this lambda term back into these equations, and you can get these accelerating universes. And that's in particular where that model comes from. Beyond those things that I talked about, which were sort of the first evidence for dark matter and the first evidence for dark energy. So conclusions. So I've talked about things we don't yet understand in physics, but the other point I guess I wanted to get across is that if something is science, if we're asking these questions, the questions that we're asking or theories that purport to explain those things, they need to be testable, they need to be provably wrong, or else it's not science, it's not a scientific question. These days, we're running into these questions that we find hard to explain. But there's a lot of open questions here, and there's a lot of ongoing work in all of these. I've really only touched the very basic surface of all of these things. So there's a lot more to do, which is why everyone should pay their taxes, and we can keep doing this. I'll leave it there. Thank you very much.